So let's talk about what might just be the most important tool we have for explaining AI today. It's a method called Shap, and its origins are pretty surprising. Not from computer science, but from 1950s game theory. And really, it answers the most human question you can ask of an AI. How much did each individual factor contribute to this specific prediction?
I mean, really think about that for a second. When an AI model approves or denies a loan or a mortgage or even helps with a medical diagnosis, that's not just code running on a server. It's a decision that can have huge consequences for a real person. So how do we get to peek inside that so-called black box to make sure its logic is sound and, actually fair?
Well, the answer began to take shape decades before modern machine learning was even a thing. A mathematician by the name of Shap was tackling a very human problem. When a team works together to win something, how on earth do you divide up the prize money fairly?
What he came up with is what we now call the Shapley value. The core idea is brilliant in its simplicity. To figure out a player's true worth, you see how the team does with them and without them. But, and this is the key, you do this for every single possible combination of teammates. A player's final Shapley value is just their average contribution across all of those different scenarios. Now here's where things get really clever. Shap takes that exact same logic and applies it directly to machine learning. So the players in the game become the features in a model, things like someone's age, their income, or their credit score. And the fair share of the winnings? Well, that becomes their fair contribution to a prediction. It's a direct and really powerful translation. What makes the Shapley value the absolute gold standard is that it's the only method that can mathematically guarantee these four properties of fairness. Efficiency just means all the contributions add up perfectly to the final outcome. Symmetry means if two features contribute the same amount, they get the same credit. The dummy property is common sense. If a feature has zero impact, it gets zero credit. And additivity means it all works whether you look at features one by one or in groups. Altogether, they create a system that is just uniquely robust and fair.
Okay, so that's the theory. But let's see how this actually works for a real person. Let's follow the story of Anna. She's just applied for a loan, and an AI model has spit out its decision. The model predicts that Anna has a 78% chance of defaulting on the loan. Now that's a high number, but on its own, what does it even mean? It's just a number. It's an answer without an explanation. Now, to put that into perspective, the average risk for all applicants is 35%. So the model sees something in Anna's profile that pushes her risk 43 points higher than that baseline, and Shap's whole job is to tell us exactly where that 43-point gap comes from.
So let's build Anna's prediction story, piece by piece. We start at that baseline risk of 35%. Right away, Shap finds the single biggest factor pushing her risk up, a high debt-to-income ratio. This one feature alone adds a massive 30 percentage points. Okay, what's next? The model looks at her income, which is on the lower side. That adds another 15 points to her predicted risk. So you can already see the main drivers of the model's decisions starting to take shape. But it's not all bad news. Anna has a really long and stable credit history, and that works in her favor. Shap calculates that this feature actually pushes her risk down by 8 points. And this shows just how well Shap handles both the good and the bad influences. Finally, her age adds a modest 6 points. And here's the brilliant part. This perfectly illustrates that efficiency property we talked about. If you add up the contributions, plus 30, plus 15, minus 8, plus 6, you get exactly 43. Add that to the 35% baseline, and we land precisely at Anna's 78% prediction. Everything is accounted for. And this is the whole point. The black box is now wide open. Anna isn't just a number anymore. She is a clear step-by-step story. She can understand the decision, she can challenge it, and she knows exactly which factors mattered most. But the power of Shap doesn't stop with just one person. What we just walked through was a local explanation, specific to Anna. But here's the cool part. We can combine thousands of these local explanations to get a global view of how the model behaves across everyone. So how do we do that? Well, it's actually pretty simple. We just take the average impact, the average Shap value for each feature across every single person in the dataset. This gives us a mathematically solid ranking of which features are the biggest movers and shakers for the model as a whole. Now, there's a catch. Calculating these exact Shapley values can take a ton of computing power. To get around this, a whole family of optimized Shap algorithms has been created. TreeShap is super fast and precise for popular models like XGBoost. If you don't know anything about the model you're explaining, Kernel Shap is a universal model-agnostic tool, even if it's a bit slower. And of course, there are specialized versions for neural networks and even simple linear models.
Okay, but this is where the conversation gets really serious. This is where explainability meets responsibility. What happens when our global view shows us that the model's most important feature is something that seems neutral, like a postcode, but is actually hiding a much bigger problem?
A model might be explicitly forbidden from using a protected attribute like race. But if it learns that postcode is a great predictor, it might just be using it as a stand-in, a proxy for race. It could be accidentally learning and perpetuating historical biases from things like housing segregation. And this, right here, is probably the most critical takeaway from all of this. Shape is not a magic wand. It doesn't automatically fix a biased model. Its job is to be a spotlight. It shines a light on what the model's actually doing, warts and all. Because once a bias is found, once you can see it and point to it, you can actually do something about it. You can question why that feature is being used, or retrain the model on fairer data. Seeing the problem is always the first, most critical step.
At the end of the day, explaining our AI systems isn't about proving that they're perfect, because no complex model is. It's about making them accountable. It's about building systems whose decisions we can inspect, question, and, when we need to, correct.
And that is why Shape is so incredibly powerful. It delivers on these three essential pillars: a mathematically fair way to assign credit, true visibility into how a model works, both for one person and for everyone, and the foundation for genuine accountability. It has absolutely earned its title as the gold standard.
Shape gives us the tools to not just take an AI's answer at face value, but to understand it, to question it, and ultimately to hold it accountable. It turns a black box into a conversation, and that, right there, is the power of transparency.